Hi, I am Alexey Pantelеев, and in this section I will talk about using the cooperative vector features efficiently on NVIDIA hardware. The most important concept to understand when talking about efficiency here is how cooperative vector operations map to the hardware execution units. Young already talked about it in the previous section, but it's worth reiterating. NVIDIA GPUs have dedicated tensor cores that perform matrix-matrix multiplication in low precision, such as 16-bit or even 8-bit float. But the cooperative vector API only exposes matrix vector multiplication. So, to map that matrix vector multiplication to the matrix multiplication hardware, we leverage the fact that the GPU operates on groups of threads called waves or warps simultaneously, and the single matrix multiplication is handled by an entire warp. When you look at a combination of matrix vector multiplications from multiple threads, it's easy to see that the vectors can be just stacked together, and the multiple matrix vector multiplications turn into a single matrix multiplication. But there is a catch, and it's called divergence. Let me remind you what divergence is first, and why it is bad. Like I mentioned, NVIDIA GPUs group threads into groups of 32 called warps, sometimes referred to as waves or subgroups. AMD and Intel GPUs have similar concepts. In this course, we're using the term wave for consistency, and this is what slang uses also. A single SM or streaming multiprocessor takes instructions from the program one by one and executes each of them on all 32 threads at the same time. But the program usually assumes that it doesn't happen, that every thread is independent. So, what happens when different threads in a wave follow different execution paths? The answer is that all execution paths taken by different threads are serialized. In the example on the right, some threads take the first batch of the if and some take the second one. The SM will sequentially execute code from both branches, keeping some execution units inactive in both cases and then synchronize. This is obviously suboptimal and should be avoided to achieve best performance. Similar serialization happens when threads in a warp access memory in a suboptimal pattern. The optimal memory access pattern is when all threads in a wave access data within one cache line. For example, a wave collectively loads 32 consecutive integers from memory. If threads access memory all around the place, accesses to separate cache lines are internally serialized by hardware and work slower than the optimal patterns. Why am I telling you all this? Because cooperative vector operations have very similar performance effects from divergence. The root of the divergence problem here is that tensor cores compute a single matrix multiplication for the entire wave, meaning that both A and B matrices are shared by all threads. But the CoopVec programming model doesn't make such restrictions. Every thread is allowed to perform its own separate matrix vector multiplication or not perform anything at all. For the situation when some threads are inactive, we have a simple solution. We can wake up the inactive threads temporarily. But if they are using different matrices, that's a bigger problem. To solve that problem, we can detect the groups of threads that use the same matrices and loop over the groups, processing each group separately. This means that divergence in matrices used for the CoopVec operations is internally serialized, just like divergent code paths or memory accesses. Obviously, this serialization comes at a significant cost. The plot on the right shows how relative performance, expressed as percentage of ideal tensor core utilization or speed of light, depends on the divergence, or more specifically on the size of thread groups that share a matrix in a CoopVec operation. Note that the plot is using double logarithmic scale. On the left, when the thread groups sharing a matrix are large, it doesn't really matter. Performance starts to degrade when the matrix data stops fitting into the L1 cache, and then keeps dropping linearly in this double logarithmic scale. To keep performance high, try to avoid CoopVec operations that end up using different divergent matrices. Group draw calls by material, sort threads manually, or use shader execution reordering. The second important implication of tensor core usage is matrix layouts. You see, tensor cores in NVIDIA GPUs expect input matrix data to be arranged in a custom, non-intuitive way that depends on the matrix element type and GPU architecture. In order to satisfy that requirement, matrices originally stored in a row major or column major layout in memory, or coming from the input vectors in CoopVec operations, must be shuffled. The output of the tensor core operations are also stored in a custom layout and must be shuffled back into appropriate threads. Good news is that some of these shuffles can be done offline, and some may be omitted because the output of the tensor core operation can be directly used as an input in another operation without any layout changes. The matrix input to the Cooperative operations comes from memory and can be stored in the correct layout there, avoiding the need for shuffles in the shader. But since the specific layout depends on the GPU and data type, the conversion must be done at application runtime. You shouldn't store converted matrices on disk. The first step in the layout conversion process is to query the size of the converted matrix from the driver. In some cases, the optimal matrix layout takes more memory than the row or column major layout with optimal packing. Then the source matrix data needs to be uploaded to the GPU, and the conversion is performed on the GPU in a command list or command buffer. There are two optimal layouts, inference optimal and training optimal, and then they can be used in matrix vector multiplication and outer product operations respectively. The converted matrix is then stored in GPU memory in a buffer and is directly provided to the Cooperative functions, along with a parameter specifying the layout. The APIs that perform size queries and conversions are shown on this slide for reference. On Vulkan, the same function performs CPU side conversion and returns the output size if you call it with a null output buffer. On DX12, there is a dedicated size query function, but no CPU side conversion function. That was the matrix operand, but what about the input and output vectors? The inputs are typically assembled in local variables, not memory, and the outputs also land in local variables. So they must be shuffled into Tensor Core compatible layouts by the shader. Let's take a look at a small code snippet implementing a 3-layer MLP with reload activation and see how its code is transformed internally by the compiler to make it work on Tensor cores. First, input and output shuffle operations are added before and after each matrix vector multiplication operation. This makes the code functional, but the shuffles are expensive and their number should be minimized. Fortunately, like I mentioned, the layout of Tensor Core outputs is compatible with Tensor Core inputs. If the compiler detects an unshuffle and shuffle pair with simple element-wise operations on the vector between them, this pair can be safely removed. The process of removing these redundant pairs is called layer fusion, and it's somewhat fragile. Sometimes the compiler cannot detect that the shuffles can be removed safely and leaves them in. That leads to poor performance. I'll talk about how to prevent layer fusion failures a little bit later. Finally, if the compiler cannot statically determine that all threads will for sure use the same matrix, it implements this divergence peeling loop. The loop is dynamic, and if there is no divergence at runtime, it will only execute once, but the extra code and branch operations still have some minor cost. Now, going back to layer fusion and its fragility. Unfortunately, at this time there is no publicly available tool to diagnose whether layer fusion succeeded or failed. We're working with the on-site graphics team to add this functionality, but right now it's not there. For now, I can recommend an experimental approach. First, measure the performance of your code as is. Then remove all code between the Cooperative matrix operations, such as activation functions. Ideally, performance should improve, but not too much. If you see something like a 2x speedup, that likely means that layer fusion failed due to some of the disabled operations. So, reintroduce these operations one by one and see which one is responsible for the perf cliff. Of course, the output of the neural network with these modifications will be incorrect. I can also give you some general advice on how to write code to avoid layer fusion failures. The most important bit of advice here is that all operations on vectors between matrix multiplications must be done in vector form. For example, instead of the loop shown on the left applying leaky reload activation to each vector element individually, use a single max operation on the entire vector. For more complex activation functions, this conversion might be non-obvious, but usually the min, max, and especially step intrinsics are enough to express piecewise functions with some creativity. Another important aspect of ensuring layer fusion success is using vector loads, such as for bias or scale vectors. The concept is the same. Instead of element-wise loads, use a vector load intrinsic. In case of a simple bias operation, though, it's even better to roll it into the Cooperative matmul add operation, if possible, which allows the compiler to pick the most optimal implementation. Finally, I'd like to say a few words about math precision and how it affects performance. There are three main levels of precision available on Cooperative operations on NVIDIA GPUs: 8-bit integers, 8-bit floating point in two versions E4M3 and E5M2, and 16-bit floating point. Each one has unique advantages and drawbacks. 8-bit integers are the most difficult to work with. Neural networks are trained in floating point. Converting them to integers means that quantization and custom scaling is necessary. This scaling has to be done at runtime, which introduces extra multiplication operations. More importantly, the 32-bit integer output of a mathmul operation most likely needs to be converted to 32-bit float to perform the scaling and activation operations. This introduces format conversion operations, which are relatively slow and takes many registers, and as you probably know, registers in a GPU are a scarce resource. 8-bit floating point is easier to work with and doesn't need scaling or conversions between floats and integers. For that reason, it is faster than using 8-bit integers and takes fewer registers, even though the peak throughput of the 8-bit integer and float matrix multiplications are the same. But the precision of FP8 can be insufficient for many applications. For example, an FP8 number cannot represent all integers between 0 and 255 exactly, which makes it unsuitable for the output layer in image reconstruction networks. Finally, 16-bit floating point is easiest to work with. There are no conversions necessary, and the precision is good enough in most cases. But the peak throughput of FP16 matrix multiplication is lower, making networks implemented in FP16 somewhat slower than those using int8 or FP8. Here is a comparison chart showing the relative performance of different sizes of MLPs with simple activation implemented using these three data types. As you can see, FP8 always wins in performance, but FP16 and int8 switch places when the complexity of the MLP increases. I would like to end this section with a high-level summary of the performance tips. First, use the matrix layout conversion APIs to make sure that the matrices are in the right layouts before doing inference or training. Second, structure the workload to minimize matrix divergence. Third, avoid element-wise access to vectors between MLP layers by using vector intrinsics and vector load and store functions. Fourth and final, keep in mind that layer fusion is a fragile thing and it might fail. On the right of the slide is a summary table comparing the math precision options in a qualitative way to help you decide which one to use. That's all I had to say about performance. Thank you.